Okay, so if we had 5 rectangles, again, we get our same, and we go from A to B. And since we're going over, we'll have 1 rectangle, 2 rectangles, 3 rectangles, 4 rectangles, and 5 rectangles. Which, once again, you can see that it's still too much. You'll still get a high area, but not as high. It'll only be just off a little bit less than it would be for the first 2. Okay, so to find the area for this one, you'd have to add the first rectangle and the second rectangle. Oh, that's 1. With this one, to find your approximate area, you'd have to add those 5. So R1, R2, R3, R4, R5. R1 plus R2 plus R3 plus R4 plus R5. Okay. So again, as n increases, or the number of rectangles increase, our accuracy increases. So you can imagine if you had 1,000, 10,000, 100,000, 1,000,000 rectangles, you'd get really, really close because the amount of space over would just be a little bit. So you'd be so close that that little bit of space won't make a difference. Okay. Now the rectangles that go outside of the function are called circumscribed rectangles. Rectangles over the function, we'll clean that up, are called circumscribed rectangles. And they would represent your upper sum. So they'll always give you just a little bit more than the actual area. Okay. So for this one, let's say if you have your decreasing function. If you notice for all of those, when the function is decreasing, your left endpoint is on, bring that down, is on the graph. Okay, so if you go from there, 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 so if it's decreasing, left endpoint on the function. Okay. But we can also see that if we had a graph that was increasing, and we wanted to have our graph go over it, then our right endpoint would be on the graph. All right. So any questions on that one? All right. Okay, so we're now going to look for the area. So let's say to find the area, we'll let f of x represent the following function. Okay, so let's say if we have a function here, but this one looks kind of odd, just oddly shaped function. This is our f of x. And we're looking between some points A and B. Right there. Okay, so we want to find the area of that graph. Okay, so what we're going to do is we want to pick one rectangle out of here. Okay, so the width of our rectangle, we'll call this delta x. I'll put this over here. Width of the rectangle. Okay. So let's say we want to look for and that one rectangle, let's say if you had here, that would be actually one of your lower sums, because it only goes up to the lower point and it'll miss out on that part. So we'll call that lower point of it f of m sub I, where f of m sub I equals the height of the inscribed rectangle. Okay. So this one, if we pick that one, since it goes a little bit over the graph, we'll have all that extra. We'll call that f of capital M sub I, where that's the height of the circumscribed rectangle. Okay, so we know if we had the area of the inscribed, it will be less than the area of the circumscribed. Or less than or equal to, depending on if it's a constant on that point or not. So area of circumscribed. Uh-oh, clean that up. Okay. So our area, remember, the area of a rectangle is length times width. So the area of our inscribed would be f of n sub I, which is our length, and our width is delta x. That would be less than or equal to the length of our circumscribed, which is f of capital M sub I, and our width is delta x. Okay, so we know just from those two, this will give you a little less than the area, this will give you a little more than the area. But we know that our inscribed and our circumscribed, somewhere in between is the actual area. Uh-oh, forgot my T. Okay, so it's somewhere in between there. Okay. So what if we decide that for here, we want to find the limit as your number of rectangles increase? Let n equals the number of rectangles. Now the number of rectangles, as it gets closer and closer to infinity, we know we're going to get closer and closer and closer and closer and closer and closer to that actual area. So if you put in 1 billion rectangles, or trillion, or 1 trillion squared, it's pretty safe to say you're going to be right at the area. Okay. As the number of rectangles approach infinity, the area will get closer and closer until f of your lower sum inscribed is actually equal to, actually that should be the limit. Delta x is actually equal to the limit of your circumscribed. Okay. So we know if this is equal and that's equal, by the squeeze theorem, this would have the same area. Okay, so graphically it would look like this. So you have our inscribed, which are all inside. Sorry about that. It's always going to be less than or equal to our actual area, which is exactly what the area is, not going over, not under, just the actual area. And that's always going to be less than the circumscribed, which is going to go over the actual area. Okay. So as those rectangles increase, it's going to get closer and closer and closer to this one. And as the rectangles increase here, it's going to get closer and closer to this one until they're all equal. Does that make sense? All right. Okay, so we're going to get this, and we're going to put into an actual definition. All right. Definition of the area of a region in the plane. Okay, so we'll let f be a continuous and non-negative function. On some interval a to b. Okay. Now the area is bounded by the graph of f of x, the x-axis, and the vertical lines x equals a and x equals b. Okay, so if you had a graph here, let's say we had it here, just kind of give you a visual of what they're saying. You're looking for the area between some points A and B. Those are the vertical lines they're talking about. It's bounded by the graph itself. This is the graph itself, and the x-axis. Okay, so as long as all those conditions are met, the area is actually equal to the limit of f of c of I as n approaches infinity of delta x, where our c sub I is actually between x of I and x of I minus 1. Okay, so if we actually picked a rectangle out of here, this one would be xi, this would be xi minus 1, and your c of I would be right in between. Okay. So if it's a really, really, really skinny rectangle, that c of I is right in the middle of it. Oh, forgot this part. And delta x equals b minus a over n, which is just the width of each rectangle. And n is the number of rectangles. Okay, so that gives the definition of the area, which kind of leads to just an overall general definition. Just pretty similar, but just tweaked a little bit. Okay, so the general definition just says we'll let f be defined. Uh-oh. On the interval from A to B, closed interval. And we'll let our delta be a partition of A and B, which is just saying A and B was just chopped up into smaller widths. Given by A equals x0, which is less than x1, which is less than x2, and it goes all the way to some n minus 1, which is less than our endpoint, which is b. So all we did was get A and B, chop them up into smaller rectangles, and have A be our x0, then the next one be x1, then x2, then x3, then x4, increasing as it's going to the right. At this point, our delta x of I is just the width between them. So between x0 and x1, the width between x1 and x2, it will be represented by delta xi. Of the ith subinterval. Okay. And again, if c of I is any point in between those two, oh, that brings me up. And xi minus 1, then the sum from I equals 1 to n of f of ci delta xi, where xi minus 1 is less than or equal to ci x of I. It's called the Riemann sum. Oh, sorry about that. It's called the Riemann sum. Oh, nice one. Oh, yeah, should have enough time. All right, so let's say, for example, if we're using 4 subintervals for f of x is equal to 19 plus x squared on the interval from 2 to 3, find the upper sum and round to the nearest hundred. So the first thing we're going to do, which is also the easiest thing we're going to do, is find our delta x. Okay, so on interval 2 to 3, remember, this is your A, this is your B. Okay, so we know our delta x. Oh, actually, let me get one part before that. Our 4 subintervals means our n is going to equal 4. N equals 4. So that means that delta x, which is b minus a over n, is going to equal 3 minus 2 over 4, which is 1/4 or 0.25. Okay, so that's our delta x. Okay, so that means between 2 and 3 is going to be broken down into 4 smaller intervals. Okay, so the intervals will be, we're still going to start at 2, but we're only going to go up to 2.25. Now we're going to start at 2.25, and we're only going to go up another 0.25, which would be 2.5. Now we're going to start this one at 2.5, and again, we're only going to go up 0.25 to 2.75. And then we're going to go from 2.75 to our 3. So instead of just going from 2 to 3, we just broke it down to 4 smaller intervals. Okay. Does that make sense? All right. Okay. Now the one thing you want to notice, clean that up some, that the function increases between 2 and 3. You have 19 plus 2 squared and 19 plus 3 squared. It increases. So f of x increases from x equals 2 to x equals 3. Okay. Uh-oh. So if it's increasing and we're looking for the upper sum, so we know the upper sum uses the right endpoints. Okay, so if we were to graph this, just to kind of give you a visual, let's say this is our graph here, kind of should look a little more parabolic. Close enough. I'll be here all day trying to draw this thing perfectly. Okay, so we know when x is equal to 0, your y is equal to 19. Okay, and we're looking between 2 and 3. Okay, we're looking for the upper sum, so that means our rectangle is going to go above the graph. So between 2 and 3, that should be like that. Then it goes like that. Then it goes like that. May have to move my 3 over a little bit. I'll just adjust. But that's how it should look. So you know when it's increasing and they're looking for the upper sum, your right endpoint will touch the graph. Okay. If we remember the definition, your x0 is equal to 2. This is your x1, which is 2.25. I'm going to see if I can squeeze this in here. This is your x2, which is 2.5. This one right here, just second to last, is your x3, which is 2.75. And your very last point, x4, is 3. That's what we meant by x0 is less than x1, it's less than x2, is less than x3, is less than x4. Okay, so that means that our sum from I equals 1 to n of f of c of I delta xi is going to equal the sum. We're not going to start at 0. Only reason is the right endpoint is the first one that's going to touch the graph. So because that's going to be the one to touch the graph, we're going to start at that point. So that's why we're going to start at 1. And we're going to stop at 4. So our f of c of I is just our function. That's 19 plus x of I squared. And our delta x for all of them, actually just 0.25. Okay, so move that over just a little bit because this is going to stretch out really fast. Okay, so our 0.25, remember our constant, we can bring that right out to the front. Okay, so our x1, because we're going to start at 1, is 2.25. So you have 19. Oh, yep, this should not be squared. The squared should actually be here. Because the xi is squared, not the whole thing. Sorry about that. So you have 19 plus 2.25 squared plus 19 plus 2.5 squared plus 19 plus 2.75 squared plus 19 plus 3 squared. And it's all addition, so I didn't put the, you don't have to put the parentheses, but this kind of hopefully makes it a little bit clearer. Okay, so this is actually equal,